Okay, so now we reach the final section of our linear algebra, linear relations and algebra topic, and these last three videos will be all around simultaneous equations. So I want to start off by looking at simultaneous equations from where we've just come from, which is coordinate geometry. So we want to understand that connection between what we're doing when we're solving a simultaneous equation and what's happening with the graphs. It's really important. We can learn all the algebra we want, we have to have some sense of what it is that we're actually doing. I also want to have a look at how we use CAS to solve simultaneous equations. So we're going to look at solving simultaneous equations using graphs, and also solving simultaneous equations using CAS, and a couple of different methods with CAS. So solving a pair of simultaneous equations means that we're finding the values of x and y that satisfy both equations. So let's just be clear about, so when we're solving an equation, let's say the equation is, 2x minus 3 equals 5, okay? What we're doing when we solve it and we get 2x equals 8 and we get x equals 4, is we have found the value of x that satisfies the original equation. If we substitute x equals 4 into that original equation, the equation is true. The left-hand side equals the right-hand side. When we're solving simultaneous equations, we have two equations with two unknown values, x and y, okay? And so what we're doing is we're finding the values of x and y that make both equations true, okay? So if we have the equations y equals x minus 1 and y equals 2x minus 3, the solution of these simultaneous equations is x equals 2 and y equals 1. There's two parts to the solution, okay? That's not two solutions, that is the one solution to the simultaneous equations. There are two unknowns. And that's the solution because x equals 2 and y equals 1 satisfy both equations. So in this first equation, when we let x equal 2, y ends up equaling 1. Okay, and so when x equals 2, y equals 1 for the first equation, but also when x equals 2 in the second equation, y again equals 1. So the values x equals 2 and y equals 1 satisfy both of these equations. There would be infinitely many combinations of x and y values that satisfy this equation alone. Okay, and infinitely many values of x and y that satisfy this equation alone. In fact, it'd be all the points along the line y equals x. Okay, sorry, y equals x minus 1. So over here, you've got the red line is y equals x minus 1. And every single point along that line, okay, satisfies that equation. So this point here, negative 1, negative 2. If I sub x equals negative 1, I get y equals negative 2. Okay, every single point along that line satisfies that equation. Okay, every single point along this blue line satisfies the equation y equals 2x minus 3. So for example, here's a point here at 3, 3. Okay, so if we substitute x equals 3 into the equation, 2 times 3 is 6, take away 3, y is also 3. That's a point that satisfies that equation. That's a pair of x and y values that satisfy that equation. When we're solving the equations simultaneously, we're looking for the pair of x and y values that satisfy both equations, okay? And so graphically, that's the point where these two lines cross. For both equations, when x equals 2, y is equal to 1, which means that both graphs go through the point 2, 1, and therefore that is the point where they intersect. It's really important that we understand that when we are solving simultaneous equations, we're finding the coordinates of the point where two graphs intersect. Similarly and conversely, when we are trying to find the coordinates of the point where two graphs intersect, we need to solve those equations simultaneously. And that is true not just for linear graphs, but for all sorts of graphs. If you're trying to find where two graphs intersect, you are solving their equations simultaneously. Okay, it's really important that we understand that that's what's happening when we're solving simultaneous equations. So this means that we could solve simultaneous equations using graphs. Now this is a pretty tedious and time-consuming method, and it requires you to draw accurate, precise graphs, but it's a valid method. And I want you to practice some questions like this for A, to practice your graph sketching, and B, to develop that understanding of what is actually happening when you're solving the simultaneous equations, okay? So example 1 here, we want to solve this pair of simultaneous equations, y equals 3 minus 2x and y equals x minus 3, by sketching the graphs on the axes provided. Okay, let's draw this one first, it's a bit easier. So y equals x minus 3, okay? So the y-intercept we can see is going to be when x equals 0, y is negative 3, so that's the point 0, negative 3. okay? And the x-intercept, we let y equal 0, and we add 3 to both sides, and we find that x equals positive 3. So that's the point with coordinates 3, 0, okay? So 3, 0, and 0, negative 3, and we're going to draw in a line. If you've got a ruler, use a ruler so it's nice and precise, okay? So that is the line, y equals x minus 3. And then let's do the other one. So y equals 3 minus 2x, okay? So our y-intercept, we let x equal 0, and we just get y equals 3. So that's the point 0, 3. Our x-intercept, we let y equal 0, so we get 0 equals 3 minus 2x. We add 2x to both sides, and we divide both sides by 3. So x equals 3 on 2. So when x equals 3 on 2, y equals 0. So the y-intercept of this line is 3, and the x-intercept is 3 on 2, which is 1.5. So I want to try and be fairly precise about that, okay? And again, I'm going to draw in my straight line. Got slightly off kilter there. It's going to hit through there. You can think about your gradient of negative 2, so 1 across and 2 down, just to try and draw it nice and precisely. So it is actually going to hit there. Just plotted out a few extra points. Okay, so that is the line y equals 3 minus 2x. And so we can see that they intersect here. We've got a nice precise drawing with a grid. They intersect at the point 2, negative 1. And so therefore, the solution to the simultaneous equations is x equals 2 and y equals negative 1. Okay? Now, it's not always the case that when you're being asked to solve simultaneous equations that it is because you want to find where two graphs intersect. Okay, so if the question is just solve the pair of simultaneous equations, then you don't want to give your solution as a pair of coordinates. You want to state x equals something, y equals something. However, if you're being asked to find the coordinates of the point where they intersect, you would give the coordinates of the point. Now, this question just asks us to solve the simultaneous equations. It specifies that it wants us to do so by sketching the graphs, but it's still just stating the solution to the simultaneous equations, which is x equals 2, y equals negative 1. And again, you should be able to check for both of these equations. When you let x equal 2, this equation is 3 minus 4, which is negative 1. Here, when you let x equal 2, this equation is 2 minus 3, which is also negative 1. Okay, and so it is the solution to both of those equations. Okay, so as I've said down here, and as I mentioned before we started that example, graphical methods of solution are pretty limited because they rely on accurate graphs being drawn. And obviously it's nice when the solution is a nice whole number point, but often the solution to simultaneous equations might be, 1/3 and 2/7. You're not going to be able to read that accurately off the graph. But what I want to develop here is that understanding of whenever you are solving a pair of simultaneous equations, you are implicitly finding, regardless of whether it's what's being asked for or not, you are finding the coordinates of the points, where the point or points where those two graphs intersect. Okay. Alright, so we can find the point of intersection using CAS. Okay, so we could, you've got the instructions there in your notes, but let's just talk through it back because we're going to do the same example. Oh no, it's a different example. Let's work through, I'll let you follow the notes through the things through here and have a look at that example. It's the example up here, okay, so you can get that one to work. Let's work it through for this one we've just done here in example 1, okay. So I'm going to sketch those two graphs. So I'm going to, in my scratch pad, I'm going to press the scratch pad button to go across to the graphing screen. I'm going to sketch the graph of y equals 3 minus 2x, and we'll remember from earlier discussions that f1 of x, this function notation, is in replacement of y. So we don't delete that, we leave that as it is, and in place of y, we're just going to leave it as f1 of x, and that has to be equal to 3 minus 2 times x. Okay, and our CAS draws the graph. And then I'm going to press tab to open that entry line back up, and I'm going to add a second graph as function 2. So again, I don't delete f2 of x, I just make it equal to x minus 3. And there's my second graph. Okay, so we've got the two graphs, and once you've got the two graphs, your CAS can find the point of intersection by doing menu, 6 for analyze graph, and 4 for intersection. And then it will ask you here for a lower bound. And what that wants, you can see as I move my cursor, it's a vertical line that's moving around. It wants me to indicate, to move this vertical line so it is somewhere to the left, a lower x value of the point of intersection. So I'm going to move it about here and click. And then it's going to ask me for an upper bound, and again now you can see as I move my cursor I've got a second line, and you can see it's creating this shaded region. And so what we're doing here is specifying for the CAS that the point that I'm interested in lies somewhere within this shaded region. And you can see the minute I cross over that point of intersection, it's calculating the coordinates. So I click, and then it will mark the coordinates of the point of intersection on my graph. Now obviously that's a little bit limited, because our graph is a bit limited in that the graphing screen in the CAS, it only works in decimals. So this is nice because these two graphs intersect at a nice whole number point. So it's easy, we can see that, when x equals 2, y equals -1, it's a nice whole number thing. But again, if that point was a third and 2/7, we would be getting rounded decimal values, and we always want to work exactly. Okay. So our other option, rather than doing it in the graphing screen, and I would very rarely do anything from the Analyze Graph menu in the graphing screen, because it's often quite fiddly, particularly on your handheld. Navigating those upper bounds and lower bounds can be quite fiddly, and your CAS is a bit finicky about it all. So if I wanted to find where these two graphs intersect, let me just write here. So I have in my CAS, f1 of x is the equation 3 minus 2x, and f2 of x is the equation x minus 3, and I want to find where those two things are equal to each other, okay, where they intersect. So I want to solve 3 minus 2x equals x minus 3. That's going to tell me where they cross, but I don't need to type that because in my CAS I've already got those things already called things. So I can just type, I want function 1 to be equal to function 2. And then obviously I'll need to get my CAS to solve that equation for x. So if I go back over to the calculator screen here, I can do menu 3, 1 and solve function 1 of x equal to function 2 of x for x. And it will tell me that they are equal to each other when x is equal to 2. And then obviously that's just the x coordinate of the point, so I need the y coordinate. So I'm going to need to substitute that back into one of these equations. So I can either type f2 of 2 or f1 of 2. f1 of 2, replacing the x value in function 1 with 2, and I get that y equals -1. Okay. Similarly, you should find if you subbed it back into function 2, you get exactly the same thing. Okay. So that is the solution of the simultaneous equations. All right. So let's have a look at another example here. Consider the simultaneous equations 5x minus 1 and 2x minus 7, y equals 5x minus 1 and 2x minus 7y equals 35. Use your CAS to plot graphs of these equations on the same axes. If necessary, adjust the window to ensure that the point of intersection can be seen. Use your CAS to find the point of intersection of the two graphs and hence give the solution to the simultaneous equations correct to 2 decimal places, that's part B. And then part C, by solving an equation in the calculator screen of your CAS, give the exact solution to the simultaneous equations. Okay, so let's go back over to our graphing screen. I'm going to press delete 3 times, which will ask me, do I want to delete everything? And I'm going to say yes. And then I'm going to add these two graphs. Now, the first function is 5x minus 1. Okay. Now, the second one, we have to be a bit careful here because y is not the subject here. So I can either do that rearrangement myself. Your CAS can only enter equations that are y equals something. It can do other things, but I want to discourage you from mucking around with changing the entry line. We want to get used to always leaving it in function notation. It's going to make it easier. So we want to make y the subject. Now we can do that by hand. Okay, so we can subtract 2x from both sides, so we're going to have -7y equals -2x plus 35. We can multiply everything by -1 just to make it all a bit easier. 7y equals positive 2x minus 35. And we can divide everything by 7, so y equals 2/7 x minus 5. Alternatively, you could get your CAS to do that rearrangement for you. So you could solve 2x minus 7y equals 35 for y. Get it to make y the subject. and that's the same as what we've got here. It's just got it all written over 7, so it's 2x minus 35 all divided by 7. Okay. Either way, that's the equation we want to sketch. So tab to open up my entry line again. You can either type what we've got there, or I can type what the CAS gave me, which was 2x minus 35 all divided by 7. It's the same thing. And we get our other equation. Okay, now it says use your CAS to plot the graphs, which we've just done. If necessary, adjust the window to ensure that the point of intersection can be seen. Okay, I can see my point of intersection on the screen here, but it's perhaps getting a bit close to the bottom there. It's all going to get a bit cramped. So I might decrease this value. So I'm clicking on that number once, click on it again to edit it. Let's maybe make that minus 10 just so we can see a bit more clearly where our point of intersection is. You might want to make some further adjustments. We don't need as much space over there. We certainly don't need as much space over here, whatever it might be. Okay. That's now triggered. It's changed my scale to be in units of 0.2. I might make it back to units of 1. Okay, whatever it might be. You can play around as much as you want. So it says use your CAS to find the point of intersection of the two graphs and hence give the solution to the simultaneous equations correct to 2 decimal places. So I'm going to do it in the graphing screen here, and then part C asks us to solve an equation in the calculator screen. So we're going to do menu, 6, intersection, number 4, okay, and we're going to go lower bound, upper bound, and there we've got our point. I'm just going to move it so I can read it properly. And we want to give the solution to the simultaneous equations, not the coordinates of the point, okay? So I'm going to give x equals something and y equals something. And because I'm rounding them off to 2 decimal places, they're actually approximately equal. So x to 2 decimal places is approximately equal to negative 0.85, correct to 2 decimal places. And y is approximately equal to negative 5.24, correct to 2 decimal places. Now, if you needed, let's say we needed the answers to 3 decimal places, the x value is fine, but the y value is being rounded off, and that's because my CAS is set to something called float 3, and it's showing me three digits, 3 significant figures basically. So 848 and 524. So if I wanted more decimal places, let's say in this second number, I would go to this number and I would click on it once to select it, and then I want to do a right click. Now I'm on my computer, so I'm going to have to do a right click, but you would press Control Menu to do a right click. And then I'm going to go to attributes. I want to look at the attributes of this number, and at the moment it's showing me 3 digits, and I want to increase that. So now I'm seeing 4 decimal places, 5 decimal places, etc., and you can do that as much as you want. Okay. If you needed to see more decimal places, we didn't in this particular instance. So the answer correct to 2 decimal places is that, but it's a rounded answer, it's not exact. Okay, so the calculator screen is limited in that regard. So part C says, by solving an equation in the calculator screen, give the exact solution to the simultaneous equations. So I know I want to look at when function 1 is equal to function 2. That's going to be when they cross. So over in my calculator, I'm going to solve function 1 equal to function 2 for x. And actually, I did that previously when my function 1 and function 2 were something different. But now that they've changed, if I just scroll up here, this is exactly the line I want to enter in again. I've just scrolled up by using the up arrow. I'm going to press enter, and that will copy that line down here. I can edit it if I need to, but in this instance I don't need it to. This is exactly what I want it to do. And it's not going to give me the same solution it did before, because now function 1 and function 2 are something different. So when I press enter, it's going to take the current function 1 and make it equal to the current function 2, which is these 2 functions over here. And it's going to solve them, okay? And it gives me x equals, it's not approximately equal to, it exactly equals negative 28 on 33. If we press Control Enter, we can get a decimal approximation for that, and we can see that it is indeed negative 0.85, correct to 2 decimal places, okay? And then once I've got my x value, I want to substitute that back into one of the equations. So f1 of, I want to replace the x in function 1 with negative 28 on 33. And we should be able to check if we substituted it into function 2 instead. That is the point where they intersect, and so therefore it should give the same y value. And again, if we press Control Enter to see that answer as a decimal, we can confirm it is actually the exact representation of that decimal. So the exact answer is x is negative 28 on 33, and y is negative 173 on 33. Okay, So the graphing screen is limited in that it doesn't give you exact answers, and so we want to be able to look at our graphs and see what's happening, but then come across to the calculator screen and make more exact calculations. Okay, now that's again still just developing our understanding of what's happening with graphs, and you'll certainly have situations down the track where you're going to use your CAS in that way to find the coordinates of the points of intersection between two graphs. However, if I just want to solve two simultaneous equations and I have no need to look at their graphs whatsoever, there's a much quicker way to do that. My CAS has a dedicated menu option for solving simultaneous equations. Okay, if we go to menu, 3 for algebra, 7 for solve a system of equations. We have a system of equations here, and we're always going to choose option 1 here. In this example, we could choose option 2 because our two equations are indeed linear equations. Okay, so we could choose option 2, but option 1 will work no matter what our equations are. So we've pressed menu 3, 7, 1 to solve system of equations. We then need to tell it, let's do this example that we just did in part 2 again. We then need to tell it how many equations we have. Okay, we have 2 equations, and what the unknown variables are in those equations. In this case, in example 2, they were x and y. So we don't need to change anything here. I'm just pressing tab to move through the dialog box, and I'm going to press enter on OK. And it brings up this template here. And I simply enter my 2 equations into the 2 boxes. So the first equation was y equals 5x minus 1. And the second equation, now there's no need to rearrange here. I can just enter this equation in as it was. 2x minus 7y equals 35. And there we have the solution to the simultaneous equation. So it's definitely the most efficient way if we're solving simultaneous equations when we have our CAS. However, it's important that we also understand the connection to graph and how we can use the graphing screen if we've drawn the graphs first to be able to solve the simultaneous equations. Okay, so so part D of the same example is exactly what we've just done. We used our CAS, we used this method to solve those same equations. So I am just going to take a screenshot of that and paste that over here, just so that you can refer to that down the track. Okay, so that was our method using this particular CAS method. Okay. The next thing we want to think about is we still want to maintain that connection to what we're doing when we're solving simultaneous equations is finding where the graphs cross. Now it's possible, so we've just looked at a series of examples where we've got 2 different linear graphs and they cross at one point, such as here. So when we solve those simultaneous equations, we get one solution. Now that one solution has 2 parts to it, x equals something and y equals something, but it is one solution to the pair of simultaneous equations. Okay? They're not 2 different solutions, they're 2 parts of the same solution. However, it's possible that we could have 2 linear equations that are actually parallel lines. And in that case, if we were to try to solve them simultaneously, we would find that they have no solutions. There is no point of intersection. It's also possible that the 2 lines that we're dealing with are actually the same line. We can call those coincident lines. Okay? So if they're the same line, they're going to have infinitely many solutions. And I know that might seem a bit trivial because surely if you're trying to solve, y equals 2x plus 1 and y equals 2x plus 1, it's clear that they're the same line. But we can rearrange this in lots of different ways. We could write this as y minus 2x equals 1, and we could multiply everything by 4 and have 4y minus 8x equals 4, and not recognise that actually that equation and that equation are in fact the same thing. Okay, so sometimes you might not notice it when you go ahead, you try to solve them, but it's possible that they could be the same line, and hence there would be infinitely many solutions. Okay, so in example 3 here, our last example, we want to do 3 things. We've got part A and part B, each with a pair of simultaneous equations. We want to, for each pair, in part 1, use our CAS to solve the equations simultaneously. Part 2, use our CAS to plot the graphs of the equation. And part 3, state the number of solutions to the simultaneous equations. Okay, so let's do part 1 first, which is to solve the equations using our CAS. And the best way to do that is menu 371. Okay, so again, I know we're quite new to our CAS here. So I you start to learn these menu options as menu 371, because the best way to navigate your menus is not to press menu and scroll up and down, but it is to press menu, and then if you want algebra, to just type number 3. Okay, sorry. So menu 3 for algebra, 7 for solve system of equations, and 1 for solve system of equations. Okay. We've got, again, 2 equations in terms of x and y. Oops, sorry. So I'm just going to tab down to OK. And now I've got my template, and I can put my 2 equations in here. So the first equation is y equals 3x plus 5, and the second equation is 6x minus 2y equals negative 10. Okay, now when I get my CAS to solve it, so I'm going to write this out. Okay, my CAS tells me that x equals, now that C1 is special CAS notation, it's not really maths, we just want to use a different letter. Now n is a common letter. My CAS tells me that x equals n minus 5 over 3 and y equals n. Okay, so that doesn't make a lot of sense, but your CAS isn't broken, it's actually doing exactly the right thing. Let's have a look by answering part 2 at what's actually happening with these 2 graphs. So before we can do that, we're going to need to make y the subject in the second equation. So I'm going to do a quick solve in my CAS. I'm going to solve 6x minus 2y equals negative 10 for y. Comma y. Okay. And actually, hopefully all is being revealed now. When we rearrange this to make y the subject, we find that the equation of this is also y equals 3x plus 5. Okay, and so we can see that they're actually the same line. If we were to plot our CAS, delete, delete, delete 3 times, I'm going to also go to menu 4, 5 to go back to zoom standard, because I played around with the window before. I always do that when I'm starting a new graph. Delete, 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 delete everything, and menu 4, 5 to reset the window. And then if I sketch the graph of y equals, or sorry, not y equals, the f1 of x. Now, that's a nice little thing that'll come up. I accidentally hit delete too many times then, and I deleted the equals. And it gives me an option to change things here, but I don't want to change it. I want it to be y equals, so I'm going to choose 3. No, sorry, I should have pressed cancel. Right, some of you have shown me this before. If you've got this rel x comma y, it does let you, it is more flexible in terms of how you draw the graph, but I want us to stick with function notation. So we're going to go back and press menu. We're going to go to number 3 for graph entry edit, and we're going to choose 1 function, and that will turn it back to function notation. Now, I want 3x plus 5, and then the other graph would also be exactly the same line, okay? So it doesn't have to draw them on paper, okay, but we can see when we plot them that they are the same line, or certainly just when we rearrange the equation that they're the same line. And so then part 3, if they are the same line, solving these 2 equations simultaneously means that they will have infinitely many solutions. And actually, what our CAS gave us in part 1, let's go back over here, is a way of describing those infinitely many solutions. That's what that's telling us. There's not one solution, there's a whole lot of them. And it's actually giving me a set of formulas that will enable me to generate any solution. Okay, so for example, when x is equal to 0, sorry, not x is equal to 0, when n is equal to 0, that unknown value is equal to 0, the equations become x equals negative 5 on 3, sorry, the solution becomes x equals negative 5 on 3 and y equals 0. That's one possible solution. When n equals 1, x will equal 1 minus 5, which is negative 4 on 3, and y will equal 1. When n is equal to, 0.2, for example, x will equal 0.2 minus 5, which is minus 4.8 on 3, which is minus 1.6, and y will equal 0.2. Okay, there's another pair of, another possible solution. There are infinitely many solutions, but they all fit this pattern, okay? So when your CAS gives you that, I don't want you to panic about that. I want you to understand, oh, that means they have infinitely many solutions. You don't need to do this. You don't need to find some of the many infinitely many solutions. You just need to understand that when you get a solution with an unknown value still in it, like what we're seeing there on the CAS screen, that is because there are infinitely many solutions. Okay, for part B, let's do part 1, which is to use our CAS to solve the equation simultaneously. So menu 371. Okay, two equations in x and y. My first equation is y equals 5x minus 2. Tab down to the next box. My second equation is 15x minus 3y equals 2. Okay, and my CAS tells me that that is false. So let's have a look at what's happening with those graphs. Okay, and again, we're going to need to rearrange this one first. So I'm going to get my CAS to solve 15x minus 3y equals 2 for x. Oh no, sorry, not for x, we want y to be the subject. For y. So you notice I just scrolled up and pressed enter to copy that previous entry line down and just edited the x into a y. Okay, so when we rearrange this, y is equal to 5x minus 2/3. And you might be able to see from here that both these lines have the same gradient, which means they're going to be, but they have different y-intercepts. So that means they're going to be parallel lines. If we have a look at them now, delete, delete, delete to get rid of that. Tab, the first equation is 5x minus 2. Press enter. Tab to open up my entry line again. The second equation is 5x minus 2/3. And we can see, okay, we haven't got a very good window there. Let's make this much smaller, so we can actually see what's happening. The red graph is that, and the blue graph is that. And so actually we have two parallel lines, which is why when we try to solve them simultaneously, our CAS is saying false. There are no solutions, okay? So what we have here when we look at them graphically is parallel lines, and so therefore in part 3, state the number of solutions. There are no solutions to that pair of simultaneous equations, which is exactly why my CAS said false at part 1. There are no solutions. Okay, so here I want you to, when it instructs you to solve by sketching graphs, I want you to sketch two nice, precise, accurate graphs and read off the point of intersection from your graph. So that's going to require you to work with precision to actually use an accurate scale. And then I want you to, so here you can see, you're doing a couple of different things. The building understanding exercise on page 65, I want you to do questions 1 and 2, and I want you to do those by hand, okay, by sketching the graphs. In exercise 1J on page 67, I want you to do question 1 by hand and solve by plotting accurate graphs, okay? Then I want you to do questions 8 and 9, ACEG in question 8 and question 9, and then I want you to use CAS for these last questions down here. So only using your CAS down here by hand for these things here, okay? Alright, so plenty of work to be doing.